So let's just go back down memory lane and just try to derive these and see what happens. So these are all chain rule problems. Since we're going to be doing that in reverse today, it'd be good to kind of get an idea. So we brought down the 7, we had 8x plus 1 to the power of 6, and then what did we need to do? We need to multiply by this, which was 8. So how could we antiderive this? That's the big question. So if we thought of this, what was it that we derived? That's the u, okay? So let's make the u like green, I guess, for now. So if we were trying to antiderive this, right? We're trying to antiderive, I guess it's going to be 7 times 8, so it's going to be 56. 8x plus 1 to the 6. We're trying to antiderive this. Forget about that now for a second, right? That's already over. And we're going to try to go from there. So let's see what we can do with that. How would we do it? So what I'm saying is we need to see the function, the inside thing we set to u. So u is equal to the inside usually, and it's usually a function of x, and you'll usually see an f prime of x somewhere, f prime of x somewhere, right? So in this case, our u would be 8x plus 1, and we derive that and use that to get our answer. So I'm kind of partially starting a U-substitution just to kind of give you a gist. Let's do some more like of these. So this one is sine of 5x. So let's think about this for a second. So y prime, whoops, sorry, only use that for the green. So y prime would equal cosine. We derived the outside function, we just took the derivative of that. We leave alone the inside, right? This inner part is what's going to be green, okay? And that's derivative is 5, right? So the question is, what's the integral of 5 cosine, whoops, again, trying really hard not to use the green unless we're talking about that. So what's the integral of 5 cosine of 5x dx? That's the question. Well, the integral of that is going to be, we know the integral of cosine, or the antiderivative, that's sine of 5x. And then we would have to have derived the 5x to get that 5. So this is our answer. That's our answer. Now doing that in our head might not be too bad, right? We can kind of see what it came from, but we need an algorithm. We need a way that will always work. So let's do a couple more here. Let's just derive them and see what happens. So this one is to the 1/2, right? So it's 1/2 2x plus 5 to the negative 1/2. And then we got to multiply by that inner. This is what our u is. So again, we're going to have 2, just like that. So this is y prime. Not too bad. Okay, just via the chain rule. How about y prime over here? Well, we're just going to rewrite it, right? And I like to say we take the derivative of this stuff. So this is our u, right? This is our u. So we multiply by 16x in that case. So these green things are what we're kind of looking for. We are going to actually be looking at problems like this, right? We're going to be looking at problems that look like this because they're the antiderivatives. And we're going to be trying to identify what's the thing that's green. And look at this, 8x squared right here, its derivative is there, 16x. 2x plus 5, its derivative is there. So when we integrate these, we're looking for a function and its derivative. So I haven't done any examples yet, but let's get into maybe an example and kind of go through the steps, okay? So you look at this and see what you think is the inside function or the parent function. Maybe not the parent is not the right word, but the function that has a derivative, right? The function that gets derived. So do you see a function and its derivative? Do you see an inner function? Those are the two questions you want to ask. If you have yes and yes to both of those, you underline it in green, and that's going to be your u. You might guess your u wrong, but that's okay. So step 1 is going to be to take your u and just write it out, x squared plus 1. So you see you're looking for this right here, that's your u. And then this right here is going to be your du. And there might be an extra number in here that kind of throws you off so you can't visually see it. in this case, it's kind of nice because we're going to take this derivative. So we're going to take the derivative of u with respect to x. So remember related rates, the derivative of v was dv dt, or the derivative of f was df dt, or the derivative of h was dh dt. We're going to take the derivative with respect to x, so it's going to be du over dx equals 2x. That's it. So you notice we derived this and we got that. Now, I'm going to emphasize something in red here because, so this is step 1 and step 2. So just so you have an idea. Step 1 is to find the u, right? And step 2 is to derive it. Pretty simple. But every single time we do this, we're not going to put du dx. We're going to put the dx on this side by multiplying it over. So I'm going to multiply by dx on both sides. That cancels out. And so you'll always just write u, and then you'll write du. You'll derive, and you'll put a dx there. So you see what we did. We did du with respect to x, derivative of u with respect to x. We took it, and we end up with 2x, and then we just put the dx over here. So now the u's are on the left, the x's are on the right. That's all good. So now, step 3 is to rewrite your integral with the u and potentially the du. The question is, do you see how this could be similar? So let's do this actually. Just because I want du to be blue, and that's a nice little rhyme, so du is 2x dx. So du is blue. Let's try to remember that. So I'm going to rewrite the integral, and I don't have an integral there. I have something that's squared, and then I have all this other stuff here, right, times something. And that's my integral. So let's go for our colors. So I'm going to scribble this all out just so you can have du is blue. So 3 is to rewrite the old integral down here, but I don't want you to put an x in this integral. No x in this integral. So u is this green thing, right? U is x squared plus 1. So you see how the x squared plus 1 is the u, right? I'm changing this via this set of rules over here. So if we want to put that into a box, that's great. Let's do that. These are the rules to rewrite the integral. And now, did we have a du? Du was 2x dx. So 2x dx is equal to du, right? So let's just kind of visualize that one more time. So this all right here, right, 2x dx, that was du, right? And this right here, this just right here, was u. So we should have integral u squared du, which we do, we have over here. Now, this is where it gets kind of nice. You look at what you have now here and you say, can I antiderive this pretending that it's an x, you know? Do you know the integral of x squared dx? Of course, we definitely know that integral. So now when we antiderive, we're going to have u to the third over 3 plus c. This is pretty much our answer, but it's not in x's. So what we'd like to do is go back to x's, so it's something to the third plus c. So what was u? Well, we'll go back, we'll use green, and u was x squared plus 1. All right? So that's kind of where we're at so far. Let me get an idea of where we are with pace. Wow. Okay, I'm going very slow. That's not terrible, but hopefully this is starting to make some sense. This is just the gist of this. So I'm going to keep going and still continue to go really slow because this is what I'm saying my answer is, right here. This is the answer. The question is, if this is the antiderivative, what's the derivative of this? So if we have 1/3, right, we have x squared plus 1 to the third plus c, and that's our y. What's our y prime? We're just checking it. This is a check. Well, y prime would be 3 over 3 times x squared plus 1 to the second times the chain rule, which is 2x. Now here's the deal. This is the U-substitution part, right? That's what we did with the U-substitution. That's gone. It's there. Now, you know it's not going to work out so beautifully that it's always going to be x squared and a 2x. Sometimes it'll be x squared and a 5x, but we're looking for a squared and a power of 1, or a fourth and a power of 3, or an eighth and a power of 7. We're looking for things like that. We're looking even for a cosine here and a sine here. We're looking for an ln here and a 1 over x here. A function and its derivative. A function and its derivative. Now there can be other things happening to that because the f of x in this question was x squared, right? We're taking the u and squaring it. So the function really was a squaring function. The outer function was squaring it. And it was u, and its derivative was du. Okay, so it worked because that is exactly what we had in the beginning, right? Check our problem and it works out good. So that's nice. I'll try to do another example because I can't stand to do a video with just one. So we're looking for patterns here, right? Identify the f of g of x and the g of x. So let's go with this as the g of x right here. Oops, sorry. This is like the du, right? This is like the u, right? And this, why don't we use, I don't know, red for the outside, the parent? So parent, okay? So what's the parent? What's the outer function here? Well, let's look for the u, the function and its derivative. So in the first one, I see the function to be this, okay? X to the fifth's derivative, I also see, and it's exactly as it is. It's nice, it's 5x to the fourth dx. They're kind of both included in that, right? Because the derivative has a dx in it. And now the question is, what was that outer function? The outer function was taking it to the third power, right? So there's that. So let's see here. That's pretty good. So look at these ones for a second. Maybe you can try B. I'll try this one for you. Do you see a function and its derivative? That's the question. There doesn't have to be an outer that's like doing anything. This is the question. Is secant then being squared? Is that the inside? Or is it tangent? That's the outer function, or that's the u, right? So tangent's derivative is exactly secant squared. So I want to say that this is my outer function. This is my u. When I derive tangent, I get secant squared dx. And my outer function, my red thing, right, is nothing. It's really just this to the first power. So it's not even necessary. It's irrelevant, right? So there we have it. So try B, look at that, think about it. Can you identify what the u would be in the du, and then the outer? And let's do one more here and see if we can recognize this. So here we have a sort of an issue. I want to know if you can like put a constant to like make it work. So the u, I keep saying the outer, I mean the u. The u is here, right? X to the fifth's derivative is x to the fourth. X to the third's derivative is x to the second, but it's off by a little bit, right? And tangent. So these are almost the same, right? The question is, how is this different, right? How can we make this work? So, what do we really want to have with this one? Because this is the u, right? But there's something missing because there's not a 5 here. There should be a 5 there. So where's the 5, right? It's missing. So we need to use that to kind of get us to actually solve this thing. We see the red thing is still to the third, right? And then here, there's our outer, right? And we know that there should be a 3 here. There should be a 3 in this dx. Oops. There should be a 3x squared, but there's not. So that's missing, right? And here, this tangent should just be secant squared. This shouldn't have a 2 here. So this 2 actually shouldn't even be here. So I'm going to put it on the outside and be like, why is it even there? This is an extra. And this is a missing. And this one, is this an extra or missing? It's a missing. Okay, so we're going to talk about how we get those numbers in a little bit. We'll just kind of like do some tricks to get there. So that'll probably be the end of this video. I will see you in the next one.